Look up at the night sky for just a moment, and you'll see countless stars, tiny pinpricks of light stretching endlessly into the void. But what if I told you that hidden within that vast darkness, something is calling out to us? Not with words, not with images, but with strange, repeating bursts of energy signals so powerful they've traveled billions of light years just to reach our planet. These aren't random cosmic noises. They're deliberate, mysterious, and unlike anything we've ever encountered. Some last mere milliseconds, while others repeat with eerie precision, defying every explanation science can throw at them. And the most haunting part, we have no idea who or what is sending them. For decades, astronomers have trained their telescopes on the depths of space, listening for whispers in the static. And what they've found is both thrilling and unsettling. 25 signals so bizarre, so out of place, they've rewritten our understanding of the universe. Some arrive like clockwork, pulsing across the cosmos with mathematical perfection. Others vanish as quickly as they appear, leaving behind only questions. Are they natural phenomena, the echoes of dying stars or colliding black holes? Or could they be something far more extraordinary, deliberate messages, cosmic sirens meant to catch our attention? The truth is, we still don't know, but each signal is a piece of a puzzle, a clue in what might be the greatest mystery humanity has ever faced. This is a journey into the unknown, a dive into the 25 most enigmatic signals ever detected from deep space. We'll explore the chilling patterns behind them, the theories that range from the plausible to the downright mind-bending, and the unsettling possibility that we might not be alone in the universe. Some of these signals have been heard only once, lost to the void before we could decode them. Others keep returning as if demanding an answer. So grab your curiosity and buckle up, because by the end of this, you'll never look at the night sky the same way again. One summer night in 1977, a radio telescope in Ohio picked up something that would send shockwaves through the scientific community. A signal so unusual, so inexplicable, that the astronomer who discovered it scrawled, "Wow," in red ink right on the data printout. And that's exactly what it was, the wow signal. Unlike random cosmic noise, this burst of radio waves was loud, focused, and lasted a full 72 seconds, an eternity in astronomical terms. It came from the direction of the constellation Sagittarius, and it matched the exact frequency scientists had predicted an extraterrestrial transmission might use: 1420 MHz, a quiet spot in the radio spectrum where natural cosmic interference is minimal. But here's the eerie part. Despite decades of searching, the signal never repeated. It vanished as suddenly as it appeared, leaving behind one haunting question: what caused it? Some believe it was a natural phenomenon, a freak burst of energy from a distant comet or a passing celestial body. Others argue comets don't emit such narrow, intense radio bursts. Then there's the more provocative theory that it was a deliberate transmission, a fleeting hello from something or someone out there. The signal's intensity suggests it originated far beyond our solar system, meaning if it was artificial, the technology behind it would dwarf anything humanity has ever built. The wow signal's legacy endures because it's a perfect cosmic riddle, a brief, brilliant flash of the unknown. Even today, astronomers occasionally point telescopes toward that same patch of sky, hoping to catch another whisper. But space, it seems, has chosen to keep its secrets for now. Just 10 years ago, astronomers stumbled upon a signal that shattered everything we thought we knew about fast radio bursts. Unlike the fleeting, one-off blips we detected before, this one had a name that sounded more like a spacecraft serial number, FRB 121102. But its ordinary designation hides an extraordinary truth. This was the first repeating fast radio burst ever discovered, a cosmic alarm clock that refuses to stay silent. Picture this, a pulse of radio waves so intense it outshines entire galaxies, erupting from nearly 3 billion light-years away. At first, scientists assumed it was another random cosmic event until it happened again. And again, sometimes months apart, sometimes in rapid-fire succession, FRB 121102 blinks on and off with no discernible pattern, yet unmistakable intentionality. It's as if the universe itself is tapping out Morse code from the edge of known space. The theories behind its origin read like sci-fi: collapsing neutron stars, black holes swallowing dense stellar matter, even the speculative possibility of alien megastructures harnessing unimaginable energy. But one explanation has gained particular traction: that we're witnessing the violent tantrums of a magnetar, a highly magnetized neutron star spinning so fast its magnetic field could strip atoms apart. Yet even this doesn't fully explain why FRB 121102 repeats while others don't, or why it bursts very wildly in strength. Then there's the haunting implication of its location. This signal isn't coming from empty void, it's embedded in a dwarf galaxy barely 1% the mass of our Milky Way, the kind of place where extreme cosmic events shouldn't be common. It's like hearing a scream from a tiny, quiet village where no one expected drama. Could this mean the conditions for such bursts are far more peculiar than we imagined? Or is there some fundamental physics at play that we haven't even discovered yet? Every time FRB 121102 erupts, it forces us to reconsider what's possible. It defies categorization, existing in a category of one, a cosmic rebel that refuses to follow the rules. And as we keep listening, one thing becomes clear: this isn't just a signal. It's a challenge, daring us to unravel its secrets. Before 2007, astronomers assumed the universe's radio whispers followed predictable patterns, until a graduate student named David Narkevic stumbled upon an anomaly that would rewrite the rules. Buried in archival data from the Parkes radio telescope in Australia was a burst so powerful, so fleeting, it seemed to defy physics itself. Lasting just 5 milliseconds, the Lorimer burst packed more energy than our Sun emits in 30 days, all while originating from a staggering 3 billion light-years away. At first, the scientific community met it with raised eyebrows. Could this be some bizarre glitch, an artifact of terrestrial interference or equipment malfunction? The signal was so unprecedented that even its discoverers hesitated, spending months double-checking their findings before daring to publish. What made the Lorimer burst extraordinary wasn't just its intensity, it was the way it challenged our understanding of the cosmos. Traditional cosmic events like supernova or colliding stars release energy over days or weeks. This was a celestial scream, a blink and you miss it explosion with no obvious source. Skeptics proposed wild theories. Maybe it was a microwave oven in the observatory's break room, or a passing satellite reflecting signals back to Earth. But when similar bursts were later detected by independent telescopes, the truth became undeniable. We were hearing something new, something unexplained. The Lorimer burst's legacy lies in its sheer disruptive power. It forced astronomers to confront an uncomfortable reality. The universe might be far louder, far stranger than we'd ever imagined. Before this, no one had catalogued fast radio bursts as a distinct phenomenon. Now they're a cornerstone of astrophysics, with hundreds documented and more pouring in every year. Some pulse just once, like cosmic firecrackers. Others, like the repeating FRB 121102, tease us with their regularity. But it all traces back to that first enigmatic blip, a 5-millisecond mystery that opened humanity's ears to the universe's hidden soundtrack. Perhaps most intriguing is what we still don't know. The Lorimer burst's brevity means we'll likely never pinpoint its exact origin. Was it the death cry of a hypermagnetized star, a cosmic collision too violent to comprehend, or something even more exotic lurking beyond the edge of current physics? Whatever the answer, one thing's certain: that tiny burst of static didn't just break the silence of the cosmos. It shattered our assumptions, proving that deep space still holds surprises waiting to jolt us awake. In 2003, a radio telescope in Puerto Rico picked up something that sent a jolt through the search for extraterrestrial intelligence program. A signal so peculiar it earned the clunky but unforgettable name SHB-02+14A. At first glance, it seemed to tick all the boxes for a potential alien transmission. A narrow-band radio burst centered at exactly 1420 MHz, the same frequency as the WOW signal decades earlier. But this wasn't just another cosmic blip. SHB-02+14A had a bizarre quirk. It drifted. Most natural radio sources, like pulsars or quasars, emit at fixed frequencies. This signal, though, appeared to shift ever so slightly, as if the source were moving, and not just moving, accelerating. The drift was small, just 8 to 37 Hz per second, but it was enough to make scientists sit up straighter. Could this be a transmission from a planet orbiting a distant star, its motion causing the subtle frequency change? The signal's origin point only deepened the intrigue. It came from a patch of space near a pair of dim, dying stars in the constellation Pisces, a region hardly prime real estate for intelligent life as we understand it. Yet here's where the debate catches fire. Some researchers argue SHB-02+14A was nothing more than interference, a passing satellite, an earthly microwave source, or even a glitch in the telescope's hardware. After all, the signal was faint, detected only 3 times over several months, and never again. Others counter that the frequency drift defies easy explanation. Man-made interference typically doesn't behave this way, and natural cosmic sources rarely emit such precise, narrow-band signals. Then there's the haunting proximity to those dead stars. If the signal wasn't artificial, what natural process could produce it near stellar corpses with no active planets? Some speculate about exotic physics magnetars with twisted magnetic fields, or rogue planets flung into deep space, their hypothetical civilizations clinging to survival. The truth is, we may never know. SHB-02+14A remains a tantalizing maybe, a cosmic whisper just loud enough to make us wonder, but too quiet to ever be certain. And maybe that's the point. In the search for extraterrestrial intelligence, the most enduring mysteries aren't the ones we solve, they're the ones that keep us listening. In 1974, scientists made history by beaming humanity's first deliberate radio message into the cosmos, the Arecibo message. A binary encoded transmission depicting our DNA structure, solar system, and even a stick figure of a human. It was aimed at a star cluster 25,000 light-years away, more a symbolic gesture than a serious attempt at contact. Then, 27 years later, something astonishing appeared in an English wheat field, a crop circle that looked suspiciously like a response. Dubbed the Arecibo reply, this intricate pattern near the Chilbolton radio telescope seemed to mirror the original message format, but with chilling alterations. Where the human figure once stood, the crop circle depicted a larger-headed, alien-like being. The DNA helix was rewritten with an extra strand. Even our solar system's depiction changed, showing 3 planets emphasized instead of just Earth. The precision was uncanny, sparking immediate debate. Was this an elaborate prank or something far stranger? Skeptics were quick to point out the flaws. Crop circles, no matter how complex, are undeniably human-made. The location's proximity to a radio telescope felt like an obvious nod to the original message rather than extraterrestrial intervention. And then there's the biggest hole in the theory: timing. Even if aliens near the original target star had somehow received the Arecibo message instantly and replied, physics dictates their response wouldn't reach Earth for another 50,000 years. The math simply doesn't add up. Yet, the Arecibo reply still captivates because of its eerie attention to detail. Whoever created it didn't just mimic the message, they reimagined it with unsettling creativity. The added DNA strand hints at genetic manipulation, while the altered planets could imply a home system far different from ours. It's a masterclass in cosmic horror, playing on humanity's deepest hopes and fears about contact. And that's the real power of this mystery. Whether hoax or art, the Arecibo reply forces us to confront an uncomfortable question. If we ever do receive a genuine signal from the stars, how will we tell the difference between truth and the stories we desperately want to believe? FRB 180916 isn't just another fast radio burst, it's the first one to ever whisper its schedule to us. Discovered by the CHIME telescope in 2018, this signal from a galaxy 500 million light-years away does something extraordinary. It follows a 16-day cycle like cosmic clockwork. For 4 days, it fires off bursts every few hours. Then, for 12 days, absolute silence. This isn't random static. It's a pattern, a rhythm in the chaos of the universe, and it's forced scientists to rethink everything they thought they knew about these enigmatic signals. What could possibly cause such precise periodicity? One leading theory points to a dancing duo in the cosmos, a neutron star locked in orbit with a massive companion, perhaps another star or even a black hole. As the neutron star swings around its partner, its powerful magnetic field might funnel energy into focused beams, which we detect as bursts only when they periodically sweep past Earth. It's like a celestial lighthouse blinking on and off as it spins. But here's the twist: most known neutron star systems don't behave this predictably. Their orbits are messy, their emissions erratic. FRB 180916's flawless tempo suggests something far more finely tuned. Then there's the more speculative angle: could this be artificial? The notion of alien megastructures, while controversial, persists because of signals like this. Imagine a civilization harnessing the energy of a star or black hole, their technology pulsing with intentional regularity. The 16-day cycle might align with orbital mechanics, perhaps a massive power grid or communication array positioned to transmit only during specific phases of its motion. It's a stretch, but not impossible. After all, nature rarely serves up such perfect intervals without reason. Yet the most compelling clue lies in the signal's home galaxy. Unlike the chaotic dwarf galaxy hosting FRB 121102, this burst originates in a quieter, more structured spiral galaxy, similar to our own Milky Way. That environment makes the neutron star theory more plausible, as such galaxies have the right conditions for stable binary systems, but it also raises new questions. Why don't we see more periodic bursts like this? Is FRB 180916 a rare cosmic fluke, or are we just beginning to tune into a hidden frequency of the universe? Every 16 days, as this signal flickers back to life, it reminds us how much we still don't understand. It's not just a burst of energy, it's a riddle wrapped in rhythm, a cosmic metronome ticking away in the dark. And with each cycle, it challenges us to listen closer, to decode the universe's quietest, most persistent beats. Most stars flicker predictably, their light dimming and brightening in gentle rhythms we've mapped for centuries. Then there's KIC 8462852, better known as Tabby's star, a cosmic rebel that doesn't play by the rules. Discovered in 2015 by astronomer Tabetha Boyajian, this distant star, roughly 1400 light-years away in the constellation Cygnus, behaves like nothing else in the known universe. Instead of the subtle, periodic dimming caused by orbiting planets, Tabby's star plunges into sudden, dramatic eclipses, its light dropping by up to 22% at irregular intervals. These aren't the gentle shadows of passing worlds, they're chaotic, jagged dips resembling a swarm of objects circling the star in no discernible pattern. At first, scientists scrambled for natural explanations. Could it be a vast cloud of dust or debris from a recent planetary collision? Maybe a family of comets, hundreds of them, spiraling into the star in chaotic unison. But each theory crumbled under scrutiny. Dust would glow in infrared, Tabby's star doesn't. Comets couldn't explain the sheer scale of the dimming nor its erratic timing. And then came the most provocative idea of all. What if this wasn't natural at all? Enter the Dyson swarm hypothesis. Proposed by physicist Freeman Dyson in the 1960s, the concept suggests advanced civilizations might harness a star's energy by surrounding it with vast solar-collecting megastructures. Imagine a network of orbiting panels, each absorbing starlight, their movements causing precisely the kind of irregular shadows we see with Tabby's star. It's a staggering thought, a civilization so advanced its signature could be written in the dimming of an entire sun. Of course, skepticism runs deep. Alternative explanations like an unusually active star with massive magnetic storms or an undetected gas giant with a ring system still hold weight. But here's what keeps astronomers awake at night. In 2017, Tabby's star emitted something even stranger than its dimming. Over several nights, the star's light dipped and brightened in ways that defied known physics. Some researchers reported possible anomalous radio emissions, though these findings remain hotly debated. Could these be the faint echoes of machinery, the hum of something vast and artificial at work? The truth is, we still don't know. Tabby's star refuses to be easily categorized, dancing between the possible and the seemingly impossible. Every new observation deepens the mystery rather than solves it. And that's what makes this signal, or rather, this absence of light, so compelling. It's not a burst or a pulse, but a cosmic silhouette, a shadow play on the grandest stage. Whether natural or not, Tabby's star has already done something remarkable. It's forced us to question just how strange the universe can get, and how much stranger the answers might be. In 2020, astronomers with the Breakthrough Listen project detected something that sent shockwaves through the SETI community, a narrowband radio signal at 982 MHz emanating from our closest stellar neighbor, Proxima Centauri. Codenamed BLC-1, this signal had all the hallmarks of a technological transmission. It appeared only when the telescope was pointed at the star, drifted in frequency as you'd expect from a planetary orbit, and occupied a quiet slice of the radio spectrum where natural interference is rare. For a brief, exhilarating moment, it seemed humanity might have stumbled upon the Holy Grail, proof we're not alone. But here's where the story twists. Proxima Centauri is no ordinary star. It's a red dwarf, smaller and cooler than our Sun, with a known rocky planet, Proxima b, orbiting in its habitable zone. The idea of a civilization just 4 light-years away, close enough that a two-way conversation might happen within a human lifetime, was intoxicating. Yet almost as quickly as excitement built, skepticism followed. The signal never repeated despite exhaustive follow-up observations. Its frequency drift, while consistent with a planetary origin, also matched something far more mundane: human technology. The most damning clue, BLC-1's frequency overlapped with known terrestrial radio interference. Some researchers pointed to satellites, aircraft, or even malfunctioning electronics near the telescope. Others noted that the signal's drift rate was suspiciously similar to oscillators found in everyday devices like cell phones and computers. Then came the kicker: further analysis revealed the signal was likely a harmonic, or ghost, of a much lower frequency transmission, the kind often produced by human-made electronics. It wasn't a message from Proxima b. It was probably a distorted echo of our own noise, bouncing through the telescope systems in a way that mimicked an extraterrestrial broadcast. But BLC-1's legacy isn't just about disappointment. It exposed a critical challenge in the search for alien signals: our own planet's radio pollution. As Earth bristles with Wi-Fi, satellites, and countless wireless devices, distinguishing a genuine cosmic signal from terrestrial static grows harder every year. The signal also highlighted how easily our brains leap to extraordinary conclusions when faced with the unknown. A reminder that in the hunt for extraterrestrial intelligence, patience and skepticism are as vital as imagination. Perhaps the most enduring lesson of BLC-1 lies in its name. The one suggests the first of many, a recognition that even false alarms refine our methods. Every dead end teaches us to listen more carefully, to filter more precisely. And someday, when a real signal does arrive, we'll owe part of that success to the echoes that fooled us first. In 1967, a young astronomer named Jocelyn Bell Burnell was sifting through reams of radio telescope data when she spotted something bizarre, a series of rapid, rhythmic pulses arriving every 1.337 seconds with uncanny precision. At first, the signal seemed too perfect, too artificial to be natural. The team jokingly labeled it LGM-1, short for Little Green Men, because the pulses were so regular they resembled a cosmic distress call. Imagine their mix of excitement and unease had they just stumbled upon an interstellar beacon, a deliberate signal from an advanced civilization, but the truth turned out to be even more extraordinary. LGM-1 wasn't aliens, it was the first documented pulsar, a rapidly spinning neutron star so dense that a teaspoon of its material would weigh 1 billion tons. These stellar corpses, remnants of supernova explosions, beam radiation from their magnetic poles like interstellar lighthouses. As they rotate, their beams sweep across Earth, creating the illusion of precise, repeating pulses. What initially seemed like a greeting from another world was actually the universe showing off one of its most extreme and dazzling natural phenomena. The discovery revolutionized astrophysics in ways no one anticipated. Before pulsars, neutron stars were purely theoretical. No one had proof they existed. Now we've catalogued thousands, each with its own unique rhythm. Some spin hundreds of times per second, whirling faster than a kitchen blender. Others, like the famous crab pulsar, are younger and slower, still recovering from the violent explosions that birthed them. These cosmic metronomes have become indispensable tools for testing Einstein's theories, mapping the Milky Way, and even aiding in the search for gravitational waves. Yet the LGM-1 episode holds a deeper lesson about how science grapples with the unknown. The initial leap to aliens wasn't just fanciful thinking, it was a reflection of how little we understood the universe's capacity for natural precision. Pulsars taught us that nature doesn't need intelligence to create patterns. It can engineer clocks more accurate than anything humans have built, and that's the real magic of this story. What began as a potential first contact moment became a humbling reminder that the cosmos is full of wonders we haven't even imagined, some so strange they'll fool us into thinking we're not alone. Today, the descendants of LGM-1 continue to blink across the galaxy, their rhythms unbroken. They're not calling out to us, but they're speaking all the same, telling the story of stars that refuse to fade quietly into the dark. And every time we detect one, we're reminded of that electrifying moment in 1967, when humanity stood at the threshold of discovery, unsure whether we'd found neighbors or something even more profound, the universe's own heartbeat. In 2015, the Ratan 600 radio telescope in Russia detected something that sent ripples through the astronomy community. A strong, narrowband signal pulsing from a star system 194 light-years away. The star HD 164595 wasn't just any celestial body. It was eerily similar to our own sun, slightly older but with nearly identical size and temperature. And orbiting it was at least one confirmed planet, a Neptune-sized world too close to the star to be habitable. But where there's one planet, there could be others. The signal itself was a sharp 2-second burst at 11 GHz, a frequency with little natural interference, perfect for cutting through cosmic noise. For a brief, electrifying moment, the world wondered, had we finally intercepted an alien transmission? The excitement wasn't unfounded. Narrowband signals like this are the breadcrumbs SETI researchers dream of, artificial seeming, deliberate, and quiet enough to rule out most cosmic phenomena. Add the fact that HD 164595's sun, like nature, made it a prime candidate for hosting life as we know it, and the pieces seem tantalizingly aligned. Some even crunched the numbers if the signal was artificial, and if it was broadcast in all directions rather than targeted. The energy required would demand a civilization capable of harnessing the entire output of their star, a so-called Kardashev Type II society. The implications were staggering, but as quickly as the hype built, reality intervened. When other telescopes, including the SETI Institute's Allen Telescope Array, trained their dishes on HD 164595, they heard nothing. No repeats, no echoes, just silence. Then came the most plausible explanation. The signal likely originated right here on Earth. 11 GHz is a frequency used by military and satellite communications, and the Rattan telescope's wide field of view made it susceptible to interference from passing aircraft or even secretive government tests. The final nail in the coffin, the signal never reappeared despite repeated monitoring. Without repetition, the case for an extraterrestrial origin evaporated. Yet HD 164595's signal lingers in the scientific imagination for what it represents, not proof of aliens, but the razor-thin line between discovery and illusion. It's a cautionary tale about how easily hope can outpace evidence, and how Earth's own technological chatter complicates the search for cosmic neighbors. But it's also a reminder that stars like ours are out there by the billions, each a potential harbor for worlds and perhaps voices we've yet to hear. The signal may have faded, but the question remains, if not this time, then when? FRB 190523 wasn't supposed to exist, at least not where we found it. When this fast radio burst flashed into existence in 2019, tracing its origin should have been a straightforward task, but the galaxy it came from broke all the rules. Unlike the chaotic, star-forming dwarf galaxies that typically host these explosive signals, this one was a quiet, unremarkable spiral, a cosmic suburb where nothing exciting was meant to happen. The discovery forced astronomers to confront an uncomfortable truth. The universe doesn't care about our expectations. Fast radio bursts were already enigmatic enough. These millisecond-long eruptions of energy can outshine a billion suns, yet their sources have remained stubbornly elusive. Most early detections traced back to young, turbulent galaxies where extreme cosmic events are common, colliding neutron stars, magnetars throwing tantrums, or black holes shredding matter. But FRB 190523 shattered that pattern. Its home galaxy, nearly 8 billion light-years away, was mature, sedate, and chemically evolved, the kind of place where the celestial drama had supposedly settled down eons ago. If fast radio bursts were screams from the universe's wild youth, this one was a middle-aged whisper from the quietest corner of the cosmos. So what could possibly cause such a violent signal in such a tranquil place? One theory points to an ancient magnetar, a highly magnetized neutron star born from a long-ago supernova, now lurking undetected in this seemingly peaceful galaxy. Magnetars are known to produce bursts of energy when their crusts crack under intense magnetic stress, like cosmic earthquakes, but even this explanation feels incomplete. Magnetars in quiet galaxies should be rare, their outbursts even rarer. Yet here was FRB 190523, proving that calm exteriors can hide staggering volatility. Then there's the tantalizing possibility that we're seeing multiple phenomena lumped under one label. Maybe fast radio bursts aren't a single class of event but a spectrum, some from young, frenetic galaxies, others from places like this where the physics operates differently. It's like hearing identical sirens in a bustling city and a sleepy town. The sound might be the same, but the causes couldn't be more distinct. The real lesson of FRB 190523 isn't just about diversity, it's about humility. Every time we think we've pinned down the rules of the cosmos, the universe throws a curveball. This signal, so out of place in its quiet neighborhood, reminds us that the universe still holds cards it hasn't shown us. And that's the thrill of the hunt. For every answer we find, there's another question waiting in the dark, another signal refusing to follow the script. The year was 2020 when Russian astronomers working with the Ratan 600 radio telescope detected something that made their instruments spike. A powerful, concentrated beam of radio waves emanating from the vicinity of HD 164595, a sun-like star 194 light-years away in the constellation Hercules. What set this signal apart wasn't just its intensity or its narrowband frequency, it was the way it vanished. Like a cosmic game of peekaboo, the signal appeared once, then refused to repeat despite relentless follow-up observations, leaving behind a mystery that still lingers today. At first glance, HD 164595 seemed like the perfect host for an interstellar hello. Slightly older and more massive than our Sun, it had at least one confirmed planet, a Neptune-sized world orbiting too close for comfort, but where there's one, there could be others in more temperate zones. The signal itself pulsed at 11 GHz, a frequency with minimal cosmic background noise, almost tailor-made for cutting through the static of space. For a brief, electrifying moment, the scientific community held its breath. Had we just intercepted a deliberate transmission, a beacon from a civilization potentially centuries ahead of us? But the euphoria was short-lived. When other telescopes, including the SETI Institute's Allen Telescope Array, scrambled to confirm the detection, they found only silence. No echo, no follow-up, just empty static where the signal should have been. This absence sparked a frenzied debate. Was the Ratan detection a fluke, a blip of earthly interference masquerading as something grander? 11 GHz is a frequency used by military radars and satellite communications, and the telescope's broad field of view made it vulnerable to false positives from passing aircraft or even secretive defense experiments. Without repetition, the signal's credibility crumbled, yet its story doesn't end there. What makes the Ratan 600 anomaly so compelling isn't just what we heard, but what we didn't. Unlike the WOW signal or BLC1, this detection came from a star eerily similar to our own, amplifying the what-if factor. If the signal had been artificial, the math was staggering. To broadcast a detectable signal across 194 light-years in all directions would require energy equivalent to harnessing every watt of sunlight falling on an entire planet, a feat only a Kardashev Type 2 civilization could pull off. The sheer audacity of that possibility still sends shivers down the spines of SETI researchers, yet the silence speaks volumes. In science, reproducibility is everything. A signal that can't be confirmed might as well be static, a lesson etched into the history of false alarms. But here's the twist: HD 164595 hasn't stopped fascinating astronomers. Recent studies suggest the star might host a second, Earth-sized planet in its habitable zone, a world that could in theory sustain liquid water. It's a reminder that even dismissed signals can leave behind ripples, steering our gaze toward corners of the cosmos we might otherwise overlook. The Ratan 600 anomaly now sits in a peculiar limbo, not quite debunked, not quite validated, a ghost in the machine of cosmic exploration. It's a cautionary tale about the razor's edge between discovery and delusion, and a testament to the universe's knack for keeping its most tantalizing secrets just out of reach. Perhaps one day, HD 164595 will speak again. Until then, it lingers as a whisper at the edge of our understanding, proof that sometimes the most haunting signals aren't the ones we catch, but the ones that slip away. Among all the cosmic puzzles we've encountered, few have sparked as much fevered debate as the bizarre dimming of KIC 8462852 Tabby's star. This unassuming flicker of light over 1400 light-years away in the constellation Cygnus doesn't behave like any other star we've observed. While most stars dim in predictable, gentle rhythms caused by orbiting planets, Tabby's star plunges into sudden, erratic eclipses, sometimes dropping in brightness by a staggering 22%, as if something colossal and misshapen is passing in front of it. The dips aren't just dramatic, they're chaotic, with no repeating pattern, lasting days or even weeks before fading back to normal. When astronomer Tabby first documented these anomalies in 2015, the scientific community scrambled for explanations. The obvious suspects, planets, dust clouds, or even swarms of comets, all fell short. A planet, even a gas giant, would cause uniform periodic dimming. A dust cloud would glow in infrared, which Tabby's star doesn't, and the sheer scale of the dimming ruled out comets. You'd need hundreds of thousands of them, all eclipsing the star at once to block that much light. The numbers just didn't add up. That's when the whispers began. Could this be evidence of something artificial? Enter the Dyson swarm hypothesis, a speculative but electrifying idea that an advanced civilization might construct vast energy-collecting structures around their star. Imagine millions of solar panels or habitats orbiting in tight formation, each one blocking a fraction of the star's light as they pass. The irregular dimming would make sense if these megastructures weren't perfectly aligned, their movements creating a patchwork of shadows. The concept, first proposed by physicist Freeman Dyson in the 1960s, suddenly didn't seem so far-fetched. But before we jump to aliens, the universe has reminded us it's stranger than fiction. In 2018, new observations revealed something unexpected. The star's long-term dimming wasn't just erratic, it was wavelength-dependent. Blue light dimmed more than red, a telltale sign of dust scattering. This discovery tilted the scales back toward natural explanations, particularly microscopic dust particles orbiting the star in strange, clumpy formations. Unlike the uniform dust disks we see around young stars, this dust could be the aftermath of a cosmic collision, perhaps two planets smashing together, creating a debris field that lingers for centuries. Yet even this explanation leaves gaps. Why hasn't the dust dispersed? Why does it block light so unevenly? And most perplexing of all, why did the star's overall brightness decline by nearly 3% over the span of a century, something never before seen in a star of its type? These lingering questions keep the debate alive, with some researchers still holding out for more exotic possibilities. Maybe we're seeing the remnants of a devoured planet, its shattered fragments spiraling into the star. Or perhaps Tabby's star is undergoing a phase of stellar activity so rare we've simply never witnessed it before. The real lesson here isn't just about one strange star, it's about how science grapples with the unknown. Tabby's star forces us to walk a tightrope between skepticism and imagination, reminding us that the universe doesn't owe us tidy answers. Whether the culprit turns out to be dust, aliens, or something even weirder, this cosmic enigma has already done something remarkable. It's stretched our understanding of what's possible, proving that even the quietest corners of the sky can hide the loudest mysteries. And as long as that star keeps winking at us, we'll keep watching, waiting for the next clue in this galactic whodunit. For decades, fast radio bursts were cosmic phantoms, fleeting, unpredictable, and utterly mysterious. Then, in April 2020, everything changed. Astronomers detected something unprecedented, an FRB with a return address. FRB 200428 didn't come from some distant galaxy billions of light-years away. It erupted from inside our own Milky Way, blazing across the sky from a source we already knew, a magnetar named SGR 1935+2154. This wasn't just another burst, it was a Rosetta Stone, a key to decoding one of the universe's most baffling signals. Magnetars had long been suspects in the FRB mystery. These city-sized neutron stars, born from the explosive deaths of massive stars, pack a magnetic field 1 trillion times stronger than Earth's. When their crusts crack under unimaginable strain, they unleash flares of X-rays and gamma rays, cosmic tantrums visible across the galaxy. But no one had ever caught one producing an FRB until that spring morning when multiple telescopes, from Canada's CHIME to NASA's, a swift satellite, witnessed the same magnetar erupting in X-rays and radio waves simultaneously. The correlation was undeniable. For the first time, we had proof that at least some FRBs spring from these hyper-magnetized stellar corpses. What makes FRB 200428 so groundbreaking isn't just its origin, it's the details. The signal was 1,000 times brighter than any radio emission previously linked to magnetars, yet 1,000,000 times weaker than typical extragalactic FRBs. This hinted at a startling possibility. Maybe the universe's most powerful FRBs aren't fundamentally different from our homegrown version, just scaled up to mind-bending extremes. Imagine a candle versus a wildfire, same physics, vastly different magnitudes. The magnetar's flare also offered clues about how these bursts form. One theory suggests that when a magnetar's twisted magnetic field suddenly rearranges itself, it accelerates particles to near light speed, generating shockwaves that emit both X-rays and radio waves in tandem. Yet, even with this breakthrough, puzzles remain. Why do only some magnetar flares produce FRBs? Why was this burst so much weaker than those from distant galaxies? And most perplexing of all, if magnetars explain some FRBs, what about the ones that repeat with clockwork precision or come from tranquil galaxies where magnetars should be rare? FRB 200428 didn't solve the mystery so much as crack open a door, revealing a labyrinth of new questions behind it. The takeaway is both thrilling and humbling. We now know that at least a fraction of these enigmatic signals are born from the most extreme objects in our cosmic backyard. But instead of closing the case on FRBs, this discovery flung it wide open, proving that the universe's radio whispers are more varied, more complex, and more wondrous than we ever imagined. And somewhere out there, another magnetar is winding up for its next outburst, another chance to eavesdrop on the universe's most violent tantrums. In 2020, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something that defied classification: 4 enormous, perfectly circular rings of radio emission, each spanning hundreds of thousands of light years. Dubbed strange radio circles, or ORC, these ghostly halos had no obvious source, no visible object at their centers, and no clear explanation. They weren't supernova remnants, they weren't distant galaxies, and they certainly weren't camera glitches. They were something entirely new, lurking in the gaps of our cosmic understanding. What makes these circles so baffling is their sheer scale. Each one could engulf entire galaxies, yet they emit no light outside the radio spectrum. Imagine flipping on a flashlight in a dark room and seeing only the halo of its glow, not the bulb itself. That's the essence of an ORC. Early theories ran the gamut: shockwaves from supermassive black hole mergers, ripples in space-time from colossal cosmic collisions, or perhaps the aftermath of a gargantuan stellar explosion, orders of magnitude larger than anything we've witnessed. None of these ideas fully fit. The circles are too symmetrical, too isolated, and most puzzling of all, they don't match any known phase of galactic evolution. Then came the plot twist. When researchers scoured archival data, they found similar faint rings hiding in older observations, evidence that these phenomena had been overlooked for years. That realization deepened the mystery. If ORCs are real and common, why hadn't we noticed them sooner? The answer lies in their subtlety. These rings are incredibly faint, visible only with cutting-edge radio telescopes like ASCAP, which can map vast swaths of sky with unprecedented sensitivity. It's a reminder that the universe is still full of surprises, even in plain sight. One leading theory suggests ORCs might be the aftermath of a starburst tsunami, a cataclysmic wave of star formation so intense it sends shockwaves racing through intergalactic gas. Another proposes they're the fingerprints of dark galaxies, hypothetical clusters of dark matter so dense their gravitational pull heats surrounding gas until it glows in radio waves. But the most tantalizing idea ties ORCs to fast radio bursts. Could these rings be the echoes of ancient, hyper-powerful FRBs, their energy ballooning outward over millennia like ripples in a pond? It's a stretch, but not impossible. The true magic of ORCs lies in what they represent, a frontier. Like the first hints of pulsars or the initial detection of gravitational waves, these circles signal a new chapter in astronomy, one where the universe reveals its secrets in ways we haven't even learned to anticipate. Every time we build a better telescope, we peel back another layer of the cosmic unknown, and ORCs are proof that no matter how much we think we know, the universe always has another card up its sleeve. For now, these ghostly rings remain enigmas, but their very existence is a thrilling promise. There's so much left to discover, and the next big breakthrough might be hiding in plain sight, waiting for us to look just a little closer. The year was 1998, and the Parkes radio telescope in Australia was on high alert. Astronomers had just detected a signal so peculiar, so artificial sounding, that for a brief, electrifying moment, they wondered if they'd finally found proof of extraterrestrial intelligence. Dubbed the Parkes glitch, this bizarre radio burst pulsed with rhythmic precision, appearing and vanishing at random intervals. The pattern was too consistent for a natural cosmic event, yet too erratic for any known human technology. Excitement rippled through the team until they traced the source not to the stars but to the observatory's break room, the culprit, a microwave oven. Here's how the cosmic comedy unfolded. Every time an observatory staffer heated their lunch, the telescope's sensitive equipment picked up interference from the appliance's magnetron, the component that generates microwaves. The alien signal turned out to be the hum of a reheated meal, its pulses syncing with the door being opened mid-cycle. The team confirmed the discovery by deliberately triggering the microwave while the telescope was live, replicating the mysterious bursts with hilarious precision. The incident became legendary not just for its absurdity but for the sobering lesson it taught scientists. Sometimes the universe's greatest mysteries are hiding in your own backyard, or in this case, the staff kitchen. But the Parkes glitch isn't just a punchline. It's a masterclass in the meticulous work of signal verification. Before announcing a potential extraterrestrial discovery, researchers must rule out everything: satellites, aircraft, cell phones, and yes, even kitchen appliances. The modern search for alien signals employs rigorous filtering, using multiple telescopes to cross-check detections and eliminate false positives. Yet the microwave incident underscores a deeper truth: our planet is drowning in radio noise. From Wi-Fi routers to garage door openers, Earth's technosphere creates a cacophony that telescopes must sift through like detectives at a crime scene. The glitch also highlights an ironic twist in the search for extraterrestrial intelligence. If an advanced civilization were broadcasting, their signals might resemble our own mundane tech, narrowband, pulsed, and precisely timed. The very qualities that make a transmission seem artificial also make it indistinguishable from human interference. It's a cosmic needle in a haystack problem, where the needle looks suspiciously like a stray piece of hay. Today, the Parkes microwave is enshrined in scientific folklore, a cautionary tale whispered in astronomy labs worldwide. But its legacy isn't just about laughter, it's a reminder that discovery requires humility. For every wow signal or FRB, there are 1,000 false alarms, each one teaching us to listen more carefully, to question more deeply, and who knows? Maybe one day, when we finally detect a genuine alien transmission, the first person to spot it will pause, glance warily at the nearest microwave, and double-check their data before daring to hope. After all, the universe has a wicked sense of humor, and scientists have learned the hard way to expect the unexpected, even when it's as close as the lunchroom. The universe has a funny way of toying with our expectations. Just ask astronomers who, in the late 1960s, thought they'd stumbled upon an interstellar distress call. What appeared to be a series of meticulously timed radio pulses beaming across the cosmos with near-perfect regularity turned out to be something far more extraordinary: the rhythmic heartbeat of a pulsar. One of the most famous, the Crab pulsar, spins 30 times per second, its lighthouse-like beams sweeping past Earth with such precision, it rivals the accuracy of atomic clocks. The discovery was equal parts exhilarating and humbling. Here was nature, crafting signals so unnervingly artificial, they fooled scientists into briefly entertaining the idea of alien engineers. But pulsars aren't just cosmic pranksters. These spinning neutron stars, collapsed cores of massive stars that went supernova, serve as some of the universe's most reliable navigational tools. Their pulses arrive with such predictable cadence, astronomers use them to measure vast interstellar distances. Here's how: as a pulsar's radio waves travel through the diffuse gas between stars, they slow ever so slightly, with higher frequencies arriving a fraction of a second sooner than lower ones. By measuring this delay, scientists can calculate the density of interstellar space along the signal's path, effectively mapping the Milky Way's hidden structure. The Crab pulsar, for instance, has helped calibrate distances to other galaxies, acting as a cosmic yardstick in ways its discoverers never imagined. What makes pulsars truly fascinating, though, is their diversity. While some, like the Crab, spin frenetically, others take their time. The slowest known pulsar, PSR-J0250 plus 5854, rotates once every 23.5 seconds, a glacial pace compared to its hyperactive cousins. Then there are the Black Widow pulsars, which orbit so close to companion stars that their fierce radiation slowly vaporizes them, leaving behind ghostly trails of ionized gas. These extreme variations hint at the violent lives pulsars lead, shaped by their explosive births and the crushing gravitational forces they endure. Yet the real magic lies in how pulsars bridge the gap between the mundane and the miraculous. Their pulses, once mistaken for alien messages, now guide spacecraft navigation, test Einstein's theory of relativity, and even help detect gravitational waves. It's a reminder that sometimes the universe's greatest gifts come disguised as mysteries, waiting for us to look beyond our first assumptions and see the profound truths hidden in the noise. And as we listen to these celestial metronomes, we're not just hearing the echoes of dead stars. We're witnessing the universe's own heartbeat, steady, unfaltering, and infinitely mysterious. Imagine the entire universe, every galaxy, every star, every speck of dust being pulled in the same direction by some unseen force. That's the spine-chilling mystery of the dark flow. A cosmic anomaly so baffling it suggests something vast and unknown might lie beyond the edges of everything we can observe. First detected in 2008 by astronomers studying galaxy clusters, this phenomenon defies the fundamental laws of cosmology. These clusters, along with everything else in the observable universe, are racing toward a single point in space at speeds exceeding 2 million miles per hour, and no one knows why. The strangest part, there's nothing there. No supercluster, no massive concentration of matter, nothing visible to explain the gravitational tug. According to our best models, the universe should be expanding uniformly in all directions, like a balloon inflating. But the dark flow implies something outside that balloon, something so enormous it's bending the fabric of spacetime itself. Some theorists speculate it could be the gravitational influence of another universe, a parallel reality brushing against ours in ways we can't yet comprehend. Others suggest it might be the remnants of a pre-Big Bang structure, a relic from a time before time began. Of course, skepticism runs deep. Critics argue the dark flow could be an illusion, a statistical fluke caused by incomplete data or measurement errors. But the signal persists. Subsequent studies, including observations from NASA's Wilkinson microwave anisotropy probe, have reinforced the finding, showing galaxy clusters streaming toward the same distant void like leaves caught in a cosmic current. If real, the implications are staggering. It would mean our universe isn't just vast, it's connected to something even larger, something beyond the reach of our telescopes. Here's where the speculation gets wild. Could the dark flow be a signal of sorts, not a radio transmission or light pulse, but a gravitational fingerprint left by something unimaginable? If other universes exist in a multiverse, their gravitational pull might ripple into ours, leaving traces like this. It's a stretch, but not impossible. After all, if the flow is real, then the nothingness beyond our observable universe isn't empty at all. It's teeming with unseen mass, a shadowy presence warping the cosmos on scales we're only beginning to sense. The dark flow forces us to confront the limits of human knowledge. For all our telescopes and supercomputers, we're still peering through a keyhole, catching glimpses of a reality far stranger than we ever imagined. Whether it's evidence of parallel worlds, undiscovered physics, or just a cosmic mirage, one thing's certain: the universe is hiding secrets we've only just begun to notice, and the biggest ones might lie beyond the edge of the map. In October 2017, astronomers spotted something that sent shockwaves through the scientific community: a strange, cigar-shaped object hurtling through our solar system at breakneck speed. Named Oumuamua, Hawaiian for scout or messenger, this interstellar visitor was the first confirmed object from beyond our solar system, and it behaved like nothing we'd ever seen. Most comets and asteroids follow predictable paths dictated by gravity, but Oumuamua had a secret. It was accelerating as if pushed by some unseen force. The explanation should have been simple: outgassing, the same process that makes comets speed up as sunlight vaporizes their icy surfaces. But here's the catch: Oumuamua showed no visible tail, no coma, no trace of the gas or dust that typically accompanies such acceleration. It was as if the universe had thrown us a curveball, and scientists were left scrambling to make sense of it. Some researchers, like Harvard astrophysicist Avi Loeb, raised a provocative possibility. What if Oumuamua wasn't a natural object at all? Its unusual shape, roughly 10 times longer than it was wide, bore no resemblance to the lumpy asteroids or icy comets we're familiar with. More puzzling still was its brightness, which varied dramatically as it tumbled through space, suggesting a highly reflective metallic surface. Loeb famously floated the idea that Oumuamua could be artificial, a light sail perhaps propelled by the pressure of starlight, or even a derelict spacecraft from another civilization. It was a bold claim, one that ignited fierce debate. Skeptics countered that Oumuamua's acceleration could still be explained by exotic natural processes, like the release of pure hydrogen gas, a type of outgassing that wouldn't leave a visible trail. Others pointed out that we'd never seen an interstellar object before, so of course it didn't match our expectations. The controversy only deepened when astronomers turned their radio telescopes toward Oumuamua, searching for any hint of artificial signals. The Breakthrough Listen project scanned the object across 4 radio bands, listening for whispers of technology. They heard nothing: no repetitive pulses, no narrowband transmissions, just silence. But absence of evidence isn't evidence of absence, as the saying goes. By the time we noticed Oumuamua, it was already speeding away, too distant for detailed study. Had it emitted signals earlier in its journey? Were we simply too late to catch them? The questions lingered unanswered. What makes Oumuamua so enduringly fascinating isn't just the mystery of its acceleration. It's what the debate reveals about how science grapples with the unknown. On one side, there's the cautious approach: stick to known physics, assume natural explanations until proven otherwise. On the other, there's the tantalizing allure of the extraordinary, the willingness to consider possibilities that stretch the limits of imagination. Both perspectives are vital. One keeps us grounded, the other ensures we don't miss the universe's greatest surprises by dismissing them too quickly. As Oumuamua faded into the depths of space, it left behind more than just controversy. It became a symbol, a reminder that the cosmos is stranger than we can often predict, and that some mysteries refuse to fit neatly into our existing frameworks. Whether it was a shard of an alien world, a fragment of some long-dead star, or something even more extraordinary, we may never know. But one thing's certain: the next time an interstellar visitor comes calling, we'll be watching more closely than ever, ready to unravel whatever secrets it might bring. For centuries, we've imagined civilizations so advanced they could harness the energy of entire stars. And now, astronomers may have spotted the fingerprints of such technology. Hidden in the infrared glow of distant suns, a handful of bizarre candidates have emerged, their light patterns so peculiar they've earned the nickname Dyson Sphere suspects. The concept comes straight from the pages of sci-fi. Physicist Freeman Dyson once speculated that an alien society might build vast energy-collecting structures around their star, capturing every photon of sunlight to power their civilization. If such megastructures exist, they'd emit one unmistakable signature: an excess of infrared radiation, the waste heat from all that absorbed starlight. And in the data from NASA's WISE telescope, we've found stars that match this description almost too perfectly. Take KIC 8462852, Tabby's star, with its erratic dimming that first sparked the Dyson swarm theory. But it's not alone. Stars like EPIC 204278916 and TYC 316226011 show even more extreme infrared excesses, their light curves dipping in ways that defy conventional astrophysics. Unlike Tabby's star, where dust now seems the likely culprit, these stars exhibit heat patterns that can't be explained by young debris disks or stellar flares. One of the most compelling, TYC 316226011, emits 95% of its light in the infrared, a ratio so skewed it's as if something is deliberately trapping the star's visible light and irradiating it as heat. Yet before we declare the existence of alien engineers, nature offers its own counter-arguments. Cosmic dust, especially the fine, carbon-rich variety known as polycyclic aromatic hydrocarbons, can mimic a Dyson sphere's infrared signature. When dust particles absorb starlight and re-emit it at longer wavelengths, the result is eerily similar to what we'd expect from an artificial megastructure. Even more confounding are collisional cascades, rare events where planets or asteroids smash together, creating vast temporary dust clouds that glow intensely in infrared before slowly dispersing. Could some Dyson candidates be witnessing these violent aftermaths? Then there's the sheer scale problem. Building a structure capable of enveloping even a fraction of a star requires unimaginable resources. Think dismantling entire planets for raw materials. Critics argue that any civilization capable of such engineering would likely have cleaner, more efficient energy solutions, like fusion or dark matter extraction. But proponents counter that evolution is unpredictable. Maybe harnessing starlight is a universal stepping stone. Or perhaps these megastructures serve purposes beyond mere energy collection, like computation or climate control on a stellar scale. The real intrigue lies in how these mysteries push science forward. Each Dyson candidate forces us to refine our tools, distinguishing between cosmic oddities and potential technosignatures. Projects like the upcoming James Webb Space Telescope could analyze these stars' light in unprecedented detail, searching for chemical traces that betray artificiality, unnatural ratios of elements, or the spectral fingerprints of industrial byproducts. Until then, these stars remain tantalizing maybes, their infrared whispers hovering at the edge of our understanding. Whether they're cosmic construction sites or just nature showing off, one thing's certain: they've already expanded our imagination of what's possible in the universe and what might be out there building. In the vast catalogue of cosmic oddities, few phenomena are as baffling and as breathtakingly brief as fast blue optical transients. Picture a star suddenly flaring to life, shining with an intense blue-white brilliance, only to fade into darkness within days or even hours. These aren't your typical supernova which blaze for weeks. They're not gamma-ray bursts either, though they share that same startling intensity. Fast blue optical transients, or F-bot for short, are in a class of their own, appearing and vanishing like ghostly apparitions in the night sky, leaving astronomers scrambling to explain their origins. The first F-bot to truly grab the world's attention was at 2018 Cow, detected in June 2018. Nicknamed the Cow after its randomized catalog designation, this cosmic flare erupted without warning in a distant galaxy 200 million light-years away. Over just 3 days, it blazed brighter than an entire galaxy, emitting staggering amounts of blue light before dimming as quickly as it appeared. What made the Cow so extraordinary wasn't just its speed, it was the spectrum of light it emitted. Unlike most stellar explosions, which are rich in hydrogen or helium, the Cow's light hinted at exotic materials like radioactive nickel and cobalt, elements typically forged in the hearts of collapsing stars. Yet its behavior didn't fit any known model of a supernova. Theories spiraled. Could this be a star being torn apart by a black hole, a rare type of supernova where the core collapses directly into a black hole, starving the explosion of its usual fireworks? Or something even stranger like a magnetar's birth cry, the violent awakening of a highly magnetized neutron star spinning so fast it shreds its own outer layers? Each explanation had gaps. Tidal disruption events where stars are ripped apart by black holes usually last longer and produce more X-rays. Supernova, even the most unusual ones, don't typically flare and fade this rapidly. And magnetar births, while theoretically possible, had never been observed with such intensity. Then came the twist. As astronomers scoured archival data, they found a handful of similar events, each as fleeting and enigmatic as the last. Some, like CSS 1600-15, appeared in seemingly quiet galaxies, far from the bustling star-forming regions where massive stellar explosions are common. Others, like ZTF 2018A, displayed bizarre light curves flickering irregularly like a candle in the wind. The more F-bot we discovered, the clearer it became these weren't flukes. They were a new category of cosmic explosion, one that defied our existing playbook. What makes F-bot so tantalizing beyond their sheer mystery is their potential connection to other cosmic signals. Some researchers speculate they could be the optical counterparts to fast radio bursts, the same kind of high-energy events viewed through a different lens. Others wonder if they're linked to gravitational wave detections, the visible aftermath of neutron star collisions that ripple spacetime itself. And then there's the most provocative idea of all. Could these flashes be signatures of extraterrestrial activity? It's a long shot, but not impossible. Imagine a civilization harnessing unimaginable energy, perhaps testing stellar-scale propulsion or even deliberately signaling across the cosmos. The Cow's extreme brightness and rapid decline might align with the kind of energy release such technology could produce. Of course, nature is usually the more creative physicist. The leading theories still favor natural explanations, like failed supernova or stars colliding with dense circumstellar material. But the very existence of F-bot forces us to confront how much we still don't know about the universe's most violent events. Every flash, every fleeting burst of blue light is a reminder that the cosmos is stranger than our textbooks, and that some of its most profound mysteries might be hiding in plain sight, blinking in and out of existence before we can even blink ourselves. The search for answers continues. New telescopes like the Vera Rubin Observatory will scan the skies with unprecedented speed, catching these transient events in the act. Maybe then we'll finally unravel what's behind these cosmic flashbulbs, whether they're the death throes of stars, the birth cries of exotic objects, or something even more extraordinary. Until then, F-bot remain one of the universe's most tantalizing whispers, a reminder that sometimes the most important messages aren't the ones that linger, but the ones that vanish before we can fully grasp them. In the spiral arms of NGC 6946, a galaxy nicknamed the Fireworks Galaxy for its frequent supernova, astronomers have documented one of the most baffling X-ray mysteries in modern astrophysics. Designated X1, this cosmic beacon first flickered to life in 2008, blazing with the intensity of 10,000 suns before vanishing without a trace just months later. Then, as if playing a celestial game of hide and seek, it reappeared in 2018 only to disappear again. This on-again, off-again behavior defies all known cosmic phenomena, challenging our understanding of how high-energy objects in the universe operate. What makes X1 so extraordinary isn't just its erratic timing. It's the sheer violence of its emissions. Most X-ray sources in galaxies, like neutron stars or black holes feeding on companion stars, fluctuate in brightness but never shut off entirely. X1 doesn't just dim, it vanishes from the electromagnetic spectrum completely, as if someone flipped a switch. The leading theory points to an intermediate mass black hole, a rare and elusive class of objects weighing thousands of times more than our Sun. In this scenario, X1 could be the signature of a star torn apart by the black hole's gravity, its debris flaring brightly when fresh material spirals in, then going dark once the meal is consumed. But there's a problem. Even the messiest stellar feasts don't explain the signal's abrupt total disappearances. Another tantalizing possibility involves a failed supernova. Some massive stars are thought to collapse directly into black holes without the usual explosive finale, their outer layers vanishing into the event horizon like water down a drain. If X1 marks the location of one such event, its sporadic reappearances could be the black hole sporadically snagging passing gas or dust, yet this too feels incomplete. Failed supernova should be one-time events, not recurring enigmas spanning decades. Then there's the wild card, extraterrestrial engineering. While far-fetched, the idea isn't entirely dismissed. A civilization capable of harnessing black hole energy might theoretically produce controlled X-ray bursts as a byproduct of their technology, though even proponents admit this stretches the limits of plausibility. More realistically, X1 could be revealing an entirely new class of astrophysical object, one that operates on timescales and physics we've yet to map. The Fireworks Galaxy has always been a cosmic rebel, hosting more supernova than any other known galaxy of its size. But X1 stands apart even here, a puzzle wrapped in the glow of high-energy light. Every time it reignites, astronomers race to study its spectrum, searching for clues in the flicker of its X-rays. And with each cycle, the same question lingers. Are we witnessing a natural process at the edge of our understanding, or is the universe quietly unveiling a new chapter in astrophysics, one where the rules aren't just unknown but fundamentally rewritten? For now, X1 remains an open case, its secrets locked in the rhythmic silence between bursts. But its very existence is a reminder that even in a well-mapped galaxy, the cosmos reserves the right to surprise us, to flicker, fade, and return when we least expect it, keeping the deepest mysteries just out of reach. At the heart of our galaxy, hidden behind thick veils of cosmic dust, something strange is humming. The Milky Way's core should be a predictable place, a supermassive black hole, Sagittarius a star, surrounded by swirling stars and turbulent gas. But radio telescopes have picked up an anomaly, a persistent signal unlike anything else in the cosmos. Dubbed the Galactic Center Anomaly, this eerie radio emission pulses with no clear source, no visible object responsible for its rhythmic waves. It's not the chatter of stars, not the scream of a black hole feeding, it's something else entirely, a whisper from the dark that defies every textbook explanation. What makes this signal so unsettling is its structure. Most cosmic radio waves are messy, sprawling across frequencies like static on an old television. The Galactic Center Anomaly is different. It's narrow-band, almost laser-like, as if someone or something tuned a cosmic transmitter to a specific frequency. Even stranger, it's polarized, meaning its waves oscillate in a preferred direction. a trait usually associated with highly organized magnetic fields or artificial signals. Natural processes rarely produce such clean, focused emissions, which is why this anomaly has astronomers questioning whether we're witnessing new physics or, just maybe, a signature of technology far beyond our own. The leading natural explanation points to an invisible population of magnetized filaments, thread-like structures of charged particles weaving through the galactic core. These filaments, some stretching tens of light years, could be funneling energy in ways we don't yet understand, creating focused radio waves as they interact with the Milky Way's monstrous magnetic fields. But here's the catch: no known astrophysical process explains the anomaly's precision or its eerie regularity. Some researchers speculated could be the echo of dark matter annihilations, hypothetical particles colliding and dissolving into bursts of energy. Others wonder if Sagittarius, a star itself, is playing tricks on us, its gravity bending space-time in ways that amplify or distort distant signals into something unrecognizable. Then there's the speculative edge. Could this be evidence of a Kardashev Type II civilization, a society capable of harnessing the energy of their entire star? The galactic center, with its dense stellar population and abundant energy, would be prime real estate for such a civilization. A sufficiently advanced species might use tightly beamed radio waves for communication or even propulsion, their signals leaking into space as an unintended byproduct. It's a fringe idea, but not impossible. After all, if we humans accidentally broadcast radio and TV signals into space for decades, why couldn't another civilization do the same, just on a galactic scale? The truth is, we're still groping in the dark. The galactic center anomaly resists easy categorization, straddling the line between known astrophysics and something entirely new. Every time we point our telescopes toward the Milky Way's heart, the signal persists, unchanging, as if taunting us with its secrecy. It's a reminder that even in our own cosmic backyard, mysteries lurk, waiting for the right moment, the right tool, or the right spark of insight to crack them open. And until then, the anomaly keeps humming, a siren song from the center of everything, daring us to listen closer. Deep in the archives of cosmic anomalies, there's a claim so controversial it straddles the line between groundbreaking discovery and tantalizing dead end, the so-called dark matter signal. Unlike the bursts and beacons we've encountered so far, this isn't a radio shout or an X-ray flare. It's something subtler, quieter, an excess of high-energy photons streaming from the hearts of galaxies, with energies that seem to whisper the signature of dark matter's demise. The idea is electrifying. If true, it would mean we've finally glimpsed the invisible stuff that makes up 85% of the universe's matter, not through its gravity but through its death throes. But here's the catch: no one can agree if it's real. The story begins in 2014, when astronomers analyzing data from the Fermi Gamma Ray Space Telescope noticed an odd surplus of gamma rays, light 1 billion times more energetic than visible light, emanating from the center of the Milky Way. This galactic center excess didn't match any known astrophysical source. It wasn't the work of pulsars, the usual suspects for gamma rays, because the signal was too smooth, too evenly distributed. Simulations suggested another possibility: dark matter particles colliding and annihilating each other in the dense heart of our galaxy, releasing energy as they vanished. Specifically, weakly interacting massive particles were the leading theoretical candidates for dark matter. According to the math, if WIMP exist, their mutual destruction should produce gamma rays at precisely the energies Fermi detected. The pieces seem to fit, but the universe rarely hands us easy answers. Almost immediately, alternative explanations emerged. One camp argued the excess could come from thousands of unresolved millisecond pulsars, ancient, rapidly spinning neutron stars too faint to spot individually, but collectively capable of mimicking a smooth gamma-ray glow. Others pointed to cosmic rays slamming into gas clouds near the galactic center, a mundane but plausible source of extra photons. The debate grew heated, with each new observation muddying the waters further. In 2020, a study using NASA's a new star telescope claimed to spot faint X-rays that could be linked to the same dark matter decay, adding fuel to the fire. Yet follow-up analyses found no conclusive link, leaving the signal in limbo, too intriguing to dismiss, too ambiguous to confirm. What makes this saga so compelling isn't just the science, it's the glimpse into how discovery unfolds at the frontiers of knowledge. Dark matter doesn't announce itself with flashing lights. Its signals are whispers in a cosmic symphony, drowned out by the cacophony of ordinary astrophysics. Teasing apart the real from the imagined requires painstaking work, better telescopes, sharper simulations, and a willingness to sit with uncertainty. The Fermi excess could still be dark matter, or it could be a lesson in how easily our hopes shape what we see, how the human mind excels at finding patterns even where none exist. For now, the dark matter signal remains a shadow on the data, a maybe that refuses to resolve, but that ambiguity is its own kind of gift. It keeps us questioning, probing, and refining our understanding of the universe's hidden architecture. And if there's one thing the cosmos loves, it's reminding us that the most profound truths often start as faint, flickering doubts, waiting for the right tools, the right minds to bring them into the light. In 2018, a team of astronomers made headlines with a discovery so profound it promised to rewrite the origin story of the universe itself, an elusive whisper from the cosmic dawn. Using a refrigerator-sized radio antenna in the remote Australian outback, they detected what appeared to be fingerprints of the very first stars, imprinted on primordial hydrogen gas from a mere 180 million years after the Big Bang. This signal, a subtle dip in the radio spectrum at 78 MHz, was the oldest trace of matter we'd ever observed, a relic from an era when the universe was still stumbling out of darkness into light. The implications were staggering. If confirmed, this signal, dubbed the Edge's detection after the experiment that found it, would offer a direct window into the universe's infancy, a time when the first stars flickered to life and began sculpting the cosmos we know today. These ancient suns, theorists predicted, would have bathed the surrounding hydrogen in ultraviolet radiation, altering the way it absorbed background radio waves. The Edge's team claimed their antenna had caught that very interaction, a faint but unmistakable ripple in the fabric of space-time. It was like finding a fossilized echo of creation itself. But almost immediately, skepticism erupted. The signal was too strong, twice as deep as leading cosmological models predicted. For the dip to be that pronounced, the early universe's hydrogen would have had to be far colder than anyone anticipated, or the first stars far hotter. Some theorists scrambled to adjust their equations, proposing exotic fixes like interactions with dark matter that could have sapped heat from the primordial gas. Others dug in, arguing the signal had to be contamination, perhaps a ripple from Earth's own atmosphere or an undiscovered quirk in the telescope's design. The debate grew so heated that when a second team attempted to verify the result using a different instrument, they found nothing. Just silence where Edges had heard the universe's first murmur. The mystery only deepened with time. Independent analyzers suggested the signal shape didn't quite match theoretical expectations, its edges too sharp to be natural. Then there was the timing. The cosmic dawn was thought to have unfolded over hundreds of millions of years, yet the Edge's dip implied a sudden, dramatic transition, as if the universe had flipped a switch. Was this a clue to new physics or just a flaw in the data? The controversy laid bare a fundamental truth about peering into the distant past. The farther back we look, the murkier the lens becomes, and the easier it is for noise to masquerade as revelation. Yet, even if the Edge's signal fades into irrelevance, its legacy endures. It forced cosmologists to confront gaps in their understanding of the universe's first chapters, pushing them to refine models and dream up new experiments. Projects like Hera and the upcoming Square Kilometre Array now aim to scan the same cosmic frequencies with exponentially greater precision, hunting for a definitive answer. And whether the signal was real or a mirage, it underscored a tantalizing possibility that hidden in the static of the cosmos are whispers from the edge of time itself, waiting for us to learn how to listen. The cosmic dawn may remain just out of reach for now, but the hunt for its signature has already illuminated something profound. Our relentless drive to trace the universe back to its roots, no matter how faint or fleeting the trail may be. And somewhere in that quest between the disputed data and the theoretical chaos lies a truth even more compelling than the signal itself, the realization that every answer we find only leads to deeper, more wondrous questions. From the electrifying wow signal that vanished without a trace to the rhythmic pulses of FRB 180916 ticking like a cosmic metronome, these 25 mysterious transmissions from deep space paint a portrait of the universe as anything but silent. They range from tantalizing false alarms like the microwave oven that fooled astronomers to paradigm-shifting discoveries such as the first repeating fast radio burst, which rewrote our understanding of cosmic physics. Some signals, like the haunting galactic center anomaly, whisper of invisible forces at work in our own backyard, while others, like the bizarre, strange radio circles, stretch across the void with no explanation at all. What binds them together isn't just their mystery, but what they reveal about our place in the cosmos. For every signal we've decoded like pulsars, once mistaken for alien beacons, there are a dozen more that defy categorization. The universe refuses to be pigeonholed, serving up phenomena that oscillate between the eerily deliberate and the gloriously chaotic, and that's the real magic here. These signals aren't just puzzles to solve, they're reminders of how much we don't know, how vast the gaps in our understanding truly are. Think about it, even as we celebrate detecting whispers from the cosmic dawn or mapping the dark flow's invisible tug, we're still left staring at the night sky with more questions than answers. Our fast radio bursts the screams of colliding neutron stars or something even stranger. Could Tabby's stars dimming be the shadow of alien engineering, or just a cosmic Rorschach test for our imagination? The beauty of science lies in these open-ended mysteries, the ones that keep us humble, hungry, and endlessly curious. So here's to the signals that jolt us awake, the ones that vanish before we can grasp them, and the ones still hiding in the static. Whether you're team Dyson Sphere or think every anomaly has a mundane explanation, the conversation itself is what moves us forward. Drop your favorite signal in the comments. Was it the one that got away, like the wow signal, or the one that challenged everything, like FRB 200428? And if you've enjoyed this journey through the universe's greatest hits, don't forget to like, subscribe, and join us as we keep listening to the cosmos. Because the next signal could be the one that changes everything, and you won't want to miss it.